Non-commutative constraint satisfaction problems by Hamoon Mousavi.
All right. The LSSD. I have stories and thoughts on the LSSD.
Super slow. Yeah. Right. So non-commutative CSPs.
All right. Hi, everyone. I'm Hamoon. I'm really glad to be here. I just started my postdoc at the Quantum Pod here, and finished my PhD not too long ago. And I'm going to tell you a little bit about my thesis. So we are all familiar with constraint satisfaction problems and how they are a central topic in theoretical computer science. So I'm going to tell you a non-commutative variant of CSPs that are intensely studied in quantum information. But the way I want to motivate them for you is through their relationship to classical CSPs. So if the goal is really to understand classical CSPs like Max-Cut, Max-Cut we understand very well, but other CSPs, could we gain some insight into them if we look at them through the non-commutative lens? So I prepared a few examples through which I will tell you what these non-commutative CSPs look like and tell you two really important open problems about them that I would hope to see solved. So the first one, very simple constraint satisfaction problem known as magic square game. We have a bunch of variables, non-variables, arranged in this square, 3 by 3 square, and each variable can take a value in the set -1 + 1. And there are a bunch of constraints. So in particular, we want the rows and columns to multiply to +1, except for the last column where we want the product to be -1. And the question is, can we simultaneously satisfy these constraints? Well, a moment's thought shows that this is really not possible. So by way of contradiction, suppose that we could satisfy these constraints. Then if we multiply these variables row-wise, a row first, we would get +1, and if we do it column-wise, we would get -1, and that's a contradiction. So we cannot simultaneously satisfy these constraints. But what if we try to plug in, instead of scalars, operators that mimic +1, -1? So what are these operators? This would be unitary operators with eigenvalues that are +1, -1. Could we hope to solve this problem by trying to plug in operators? So in particular, we want the product of rows and columns to be plus identity operator or minus identity operator. And just a moment ago, I gave you this contradiction that was working in the classic in the case of scalars. That same thing is true here as well. If we try to multiply these products row-wise, we get plus identity. If we try to multiply them column-wise, we get minus identity. But this is not a contradiction for operators because the order matters. We could imagine a world where product of some operators in some order is plus identity and their product in some other order is minus identity. In fact, there is a concrete assignment to these variables, some matrices that are 4 by 4 dimensional. The specifics of them doesn't matter. Here I constructed them from famous Pauli operators from quantum mechanics, and that would satisfy the constraints perfectly. Okay, and this distinction, the scalar versus operator, that we could solve this constraint satisfaction problem perfectly in the operator world, and this exact problem of magic square is at the heart of many applications in quantum information. A lot of quantum protocols start by taking this magic square and the fact that we can solve them in the realm of operators perfectly, and we cannot do that in the classical. But it has a lot of applications, for example, in cryptography, quantum cryptography. So now let me tell you about a second example of non-commutative constraint satisfaction problem. So again, we're going to start with the classical setting. It's a Max-Cut. We're all familiar with it. The goal is to find a cut that has the largest number of edges crossing the cut, right? We've all seen the formulation of Max-Cut in terms of polynomials. Let's just remind ourselves. In this formulation, we would have assigned to every vertex a variable xi that can take values +1 or -1. And doing so would allow us to have this indicator expression here that would take value 1 if and only if the assignment to xi and xj are distinct. And it would take value 0 otherwise, right? With this, it's not too difficult to see that the max-cut is really the optimization of this polynomial subject to the constraint that the variables are +1 minus 1. And now, just like magic square, the recipe for turning this into a non-commutative constraint satisfaction problem is exactly the same as before. Let's just plug in, instead of variables, these are scalars that would take +-1. Let's plug in unitaries that have eigenvalues +-1. And we ask, what would be the optimal, the maximum of the trace of such an expression that we would obtain by plugging all possible unitaries for xi and xj. Then you might say, in the case of max-cut, we had this very nice visualization. We understand what, it's a cut, and we are counting the edges. When we are assigning operators, we don't have that visualization. But still, I hope you trust me that this has a really meaningful operational interpretation in quantum information. Yes?
You still have a graph under it.
You still have a graph. Exactly. The instance is, the underlying instance is a graph. It's the same for classical and quantum. It's just that in the quantum case, you take the polynomial and you try to plug in unitaries, right? And it would have a really meaningful operational interpretation. And a simple example of this problem is actually something that physicists use day to day to calibrate their quantum devices. That simple example is called CHSH gain, for example. But as computer scientists, we want to understand which one of these problems is computationally harder. That's the first thing that we try to settle, right? Let's take a look at the problem, the classical problem, classical max-cut. It's famously NP hard, but it's decidable, right? It's just finitely many options. In the non-commutative version, though, there is no bound that we're putting on the size of these matrices, right? They could be infinite dimensional for all we know, right? So a priori, it seems that this problem could even be undecidable. And in fact, this is true. We showed that in general, non-commutative polynomial optimization is really, really hard. It's even harder, strictly harder than halving problem. Whereas, as I just mentioned, the commutative polynomial optimization is always at least decidable. It's in PS space. Okay, but this is true in general. In this specific example, actually, it turns out the non-commutative problem is easier than the classical one. In fact, the non-commutative problem is a semi-definite programming in disguise, and we can solve it in polynomial time, whereas we cannot do this for max-cut. We cannot even hope to approximate up to a constant the max-cut problem. So what is happening? Like, could we try to find like a broader class of CSPs for which this is true? In general, for any CSP, we could come up with two different relaxations for it. Just like the recipe that I gave so far, you could imagine the non-commutative CSP. By now, you know how to start from any CSP and try to come up with the non-commutative analog. And then there is the basic STP that is a relaxation to both of these commutative and non-commutative problems. Okay, and we have a beautiful theory in theoretical computer science that explains the gap between the classical value and the STP. Right? That is very well understood, very well studied. But we don't have such a theory for non-commutative CSPs. So that's what one of the things we did. We came up with a tool that would allow us to understand the gap between the non-commutative value and STP for some classes of CSPs. We can do this for CSPs that are two variable CSPs, where the equations or constraints are just involving two variables at a time, and something we call real two variables CSPs. Like for example, using this tool, a variant of max-cut problem, max-3-cut, the non-commutative version of it is, we can show that it's not too far from the value that you would get from its STP. Okay, And yeah, so I told you that this tool only works for two-variable CSPs, whereas the tool that we have for classical CSPs, like all those theories, work for any CSPs. We know that, for example, if Unigame's conjecture is true, the basic STP is always going to give you the best approximation ratio that you could hope for CSPs, for classical CSPs. We don't have such an all-encompassing theory for non-commutative CSP. This was the first step, and we hope to be able to extend that. Now, so that's one problem. The other problem is that, so I told you that there are these regimes, it seems, that where the non-commutative problem is easier to solve than the commutative one. Wouldn't it be ideal that in these cases, we could extract, once we solve the non-commutative problem, we could extract a good classical solution from this non-commutative solution? Could we hope to do something like that? Just like how in the classical theory, we could take the STP solution and then relax it or round it to a good classical solution for the CSP. Could we do that for the non-commutative solution? We showed that, yes, we could do that for Max-Cut. And already in the case of Max-Cut, the proof is non-trivial. And we have this overwhelming evidence, numerical evidence, that for all these real two-variable CSPs, this in fact is true. We could always get a good classical solution from the non-commutative solution. Also,
you're saying for Max-Cut, do you get a gap that is smaller?
So the gap is exactly the same as what you get for classical. For Max-Cut.
For STP.
For STP, exactly, it's 0.878, the Gomez-Williamson constant. But the exciting thing is that this thing that for which we don't have proof, the gap is much better than what you would get classically. Also, we are not refuting Unigame's conjecture. What happens is that this rounding technique at this point is not efficient. It just tells you that information theoretically there is always a good classical solution hidden in any non-commutative solution to these problems. I mean, we don't have proof for it, but that's a conjecture.
But you have some kind of empirical evidence?
Empirical evidence, yeah.
I see.
Yeah. And a very well-stated kind of conjecture that we were only able to prove in the case of Max-Cut so far.
And you need to only look at small dimensional non-commutative operators, or do you need to go really large dimensional?
That's the problem with why this at this point is not efficient, because the non-commutative solution could very easily become exponential size. Even in the case of Max-Cut, we can solve the problem optimally, but it could be 2 to the n, where n is the number of vertices. Dimensional matrices. Exactly. We have a small succinct representations for them. So their bit complexity is small, but they are huge matrices.
You're saying if you can solve this CSP, which could be NP hard,
yes,
then
yeah,
it's kind of like
exactly
cheating now.
I mean, yeah, you can, but I mean, so we want to know what is the gap between these two problems. We want to know whether so far it seems that the point is that the non-commutative solution is really preserving a lot of the structure of the classical problem. That's why the gap seems to be shrinking. And I think that's an interesting viewpoint. And there could be ways to make this process efficient, this rounding. At this point, we don't know how to do it, but there are ways of our rounding technique involves sampling from a hard random unitaries. And in quantum information, there are ways to do this sampling for exponentially sized matrices, but approximately efficient. So that's the kind of yeah, I'm done. That's it.
Any further questions? For those of us not well informed, what's the connection to? Can you give a one-sentence explanation of what the connection is to quantum information?
Yes. The non-commutative CSPs would capture the value of what's known as non-local gains that are central object of study in quantum information. So for computer scientists, for us, it's multi-prover interactive proofs.
Oh.
So it's essentially the value of these non-commutative problems would tell you what is the success probability of the provers in a multi-prover interactive proof. So where provers are allowed to be quantum.
Yeah.
Does that make sense? Like
Yeah.
classically, it would match the provers where we don't have we restrict them to be classical provers.
I had a question. So for any CSP, you have a sort of a trivial constant factor approximation if the arity and the domain is bounded.
Absolutely. Yes.
Is that something similar the case for non-commutative CSPs, or are there problems for which we don't know that?
All right. I think that for any CSPs, we don't even know whether this gap would be 0. Like we don't even, there's no general theory that would tell us that, that from the SDP solution you can get.
Not SDP at all, but just
Right.
if I give you a non-commutative CSP, is
Yes.
there some simple way to get some horrible constant approximation of it?
Oh no, we cannot even do that. So that's the famous result that came out, I think, in 2021. The MIT study called.
Oh, I see. So that's
That even the most modest approximation
Okay, great.
would be undecidable.
Okay.
Yeah.
Excellent.
For general CSPs.
So you mentioned that non-commutative max-cut you can solve efficiently.
Yes.
Are there other? Is there something very special about max-cut, or is there a large family of such things?
So I said that we have this tool to prove integrality gap for real two variable CSPs, but in the case of max k-cut problems, we know how to obtain this integrality gap efficiently. So we can go beyond max-cut.
But I guess to answer Nikhil's question, so for all two CSPs, the non-commutative CSP is an SDP that we can solve efficiently. Is that right?
No, for max k-cut. So max k-cuts would be a subclass of two variable CSPs. Like for example, unit games are also two variable CSPs. We don't know how to solve them efficiently. Non-commutative.
I see.
Right? So already we know that non-commutative unit games can be, there are approximation algorithms that go far beyond what we could hope to get classically. Because classically we have the unit game conjecture that tells us we cannot do better than, we cannot tell the difference between 1 minus epsilon versus epsilon. Whereas non-commutative, we can say much better, much more. We don't have an approximation. There is no approximation ratio. Like the algorithm does not give you an approximation ratio, but it is enough to refute the unit games conjecture non-commutative. Does that make sense? And max k-cut is another class of two variable CSPs, and for those we know how to solve them efficiently, approximate them efficiently, I should say.
Maybe a quick question. So,
Is there a way to solve something using some quantum computing, some relaxation which you cannot? I mean, why only classical SDP?
Right.
Can you solve some relaxation for these CSPs which is not classical or something?
I have not thought about that. That would be super exciting. Coming up with a quantum algorithm for it.
quantum algorithms for quantum problems.
That's good. What could be better?
Okay, thank you very much.
Thanks so much.
Yes, we have one more quantum talk before lunch.